January 18, 2008, London Heathrow Airport. British Airways Flight 38, a Boeing 777, is established on final approach for runway 27 left. The weather is clear, the crew is experienced, the aircraft is in mechanical compliance with every requirement placed upon it. By every measure available to anyone watching, this is a routine landing. At 720 feet above ground level, 57 seconds before touchdown, the autothrottle commands an increase in thrust. The right engine fails to respond. Its power output reduces significantly. 7 seconds later, the left engine follows. The flight crew is presented with a dual-engine rollback at a critical altitude where no recovery procedure exists. There is nothing in the manual for this, because no one had ever written one. The aircraft descends rapidly. It clears the perimeter fence by meters before impacting the turf short of the threshold. The landing gear collapses. The hull is a total loss. Of the 152 people on board, one passenger suffers a serious injury. Both engines remained running. The power was simply gone. Flight 38 had departed Beijing Capital International Airport 12 hours earlier. The Boeing 777-236ER was powered by two Rolls-Royce Trent 800 engines. The technical log showed no deferred defects. The fuel load was normal. For the first several hours of the flight, nothing happened. As the aircraft navigated westward through Siberian airspace, the fuel temperature steadily dropped. At its coldest point over northern Russia, it reached -34 degrees Celsius, still well above the freezing point of Jet A1 fuel. No warnings, no anomalies. The systems reported everything normal. But inside the fuel lines, something invisible was beginning. Jet fuel always contains trace amounts of water. This is expected. It is accounted for in the design. What was not fully accounted for was what happens to that water over many consecutive hours of cold soak under low flow conditions. The water was not freezing into solid ice. It was transitioning into fine crystals, soft and sticky and adhesive. And those crystals were quietly accumulating on the internal walls of the fuel pipes, particularly in areas where flow was slow. For hours they built, and nothing disturbed them. The fuel system architecture of the Boeing 777 includes a component called the Fuel Oil Heat Exchanger, the FOHE. Its purpose is straightforward: to use heat from engine oil to warm the incoming fuel, ensuring that cold fuel does not compromise engine performance. It was, on paper, the system's defense against exactly this kind of threat. The FOHE consists of a matrix of fine tubes through which fuel passes before reaching the high-pressure pumps. The inlet face of the unit featured tube ends that protruded approximately 4 millimeters from the header plate. Those 4 millimeters would become the mechanism of failure. As the aircraft began its descent into London, the engines throttled back to near idle. For 40 minutes, fuel demand was low. The ice crystals remained undisturbed. Then the aircraft intercepted the glide slope. The autothrottle commanded an increase in thrust. The demand on the fuel system surged sharply. The velocity of the fuel through the pipes increased, and the accumulated ice, built up across 12 hours of cold, was dislodged. Investigators would later call it an avalanche effect. The ice did not melt, it did not disperse, it traveled downstream as a mass of soft crystalline slush and arrived at the face of the FOHE. The protruding tube ends caught it, the crystals bridged the gaps. A barrier formed. Fuel flow to the high-pressure pumps was restricted. The engines did not flame out. They had fuel, but they could not access it at the rate they needed. They rolled back, to thrust barely above idle, at 720 feet, on final approach. The AAIB led the investigation, supported by the NTSB, Boeing, and Rolls-Royce. The immediate challenge was that by the time the engines were inspected, all physical evidence had melted. Investigators turned to the data. The digital flight data recorder confirmed that the engines were demanding fuel the system could not deliver. A statistical analysis of over 175,000 previous 777 flights showed that the specific environmental profile of Flight 38, a long cold soak combined with a low-flow descent followed by a high-demand thrust increase, was without precedent in the dataset. The system was certified. It met every standard written for it. The standards simply had not accounted for this. The redesign was immediate. Rolls-Royce modified the FOHE for the Trent 800. The protruding tube ends were made flush with the header plate. Inlet crimps removed. No protrusions for crystals to catch on. The Boeing updated the airplane flight manuals to mandate periodic high thrust pulses during long cold-soaked descents designed to dislodge accumulation before final approach. The FAA and EASA issued airworthiness directives requiring the modified hardware across the affected fleet.